Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 17. Today we will look at the small signal model of bipolar transistors and see how it is formed and how it plays a role in the analysis and design of circuits. So just to refresh your memory from last time, let's take a look at what we studied. We talked about large signal and small signal operation, and we wanted to distinguish between these two cases. We said that if we have a bipolar transistor with a certain amount of bias, remember that we have to bias a transistor to have a reasonable amount of current through it and hence a reasonable amount of transconductance. Then we said that we have a certain amount of bias for the base emitter, and of course the collector has to be sufficiently high to ensure that the collector base does not get forward biased. And then superimposed on this bias value, on this fixed voltage, we have some sort of signal, for example, from a microphone. Now what we observed was that if we plot IC as a function of VBE, which happens to be the bias voltage plus the signal voltage, the microphone voltage, we observe that as the signal voltage goes up and down around this bias value, the current of course also fluctuates up and down. And we saw that if this signal amplitude is small enough, then we can approximate this part of the exponential function by a straight line. And that allows us to write the output fluctuation as just a constant number times the input fluctuation. So in this case, the current fluctuation at the output is just a number times the input fluctuation, input voltage fluctuation. And what we saw was that the total current that we observe here in this regime is equal to the bias current, which we called IC0. That's the current flowing through the transistor when there is no signal. The signal is 0, just due to the bias voltage, plus a fluctuation, which is given by the slope, which is GM, times the input voltage fluctuation. So we see that the total current at the output is given by IC0, the bias value, and on top of that we have GM times the input voltage, Vm sine of omega t. So this tells us that if the signal amplitude is small enough, then we can make this approximation, and then the output can be written as Gm times the input voltage, the output current fluctuation. So it's important to remember the conditions that allow us to make this approximation. All right, but in general, this is what we have. We have a general model for the transistor, which we call the large signal model, not necessarily because the signals are large all the time, but just to emphasize that this model is valid for any voltage that we want to have here or any voltage here, provided, of course, that we are always in the forward active region. And in this case, the dependence of the current upon these voltages is more complicated because we have an exponential here. So this model is called the large signal model of the transistor. And this is to emphasize that we can have large signals everywhere. This operation that we envisioned here is called small signal operation, to emphasize that the change in the current as a result of the signal voltage is small. This fluctuation is small compared to the current that we have. That's how we define small. And for example, we want the current fluctuation to be, let's say, only 10% or 5% of the bias value. And another way of looking at it is for this approximation to come out, if you remember from last time, the amplitude of this fluctuation in the voltage that comes here should be a small fraction of Vt, 26 millivolts. So a few millivolts would be considered small for this voltage. Okay, so what we have now are large signal operation, meaning this is not limited to what I just said. This can be large, and if it's large, this current will also go all over the place. Certainly, it will have significant variation compared to the bias value. That's large signal operation, according to the large signal model. Or we can have small signal operation, meaning that the signal that's coming in is small. We can make this linear approximation. We can have this output. So the question is, if we know that the signals are small, can we have a model for the transistor that represents that small signal operation? This is the model for large signal operation, any level that wants to come in. But if we have small signals, can we simplify this model? So that's what we would like to accomplish today. All right. So today we'll talk about the small signal model of the bipolar transistor, and then we'll go over an interesting effect that happens in bipolar transistors called the Early effect. Early is the name of the person who discovered this effect. And then we will try to also reflect this phenomenon in the model. So we will arrive at a complete small signal model. All right, so let's begin with the small signal model and see how that comes about. So small signal model. All right, so let's review what we have done. We have a bipolar transistor that has a certain bias voltage. We have seen that we need a bias voltage to have a reasonable current through the device. Otherwise, we get nothing. So here's a bias voltage. We call this V0. And we have a certain collector current. We call that IC0. And of course, we need another voltage here to make sure that the collector base is, for example, reverse biased. So that's what we call VCE. All right, now I would like to apply a signal to this circuit, a microphone signal. So here's a microphone signal that goes in series with the bias voltage, so that the base emitter voltage is now the bias voltage plus the microphone signal. I don't want to write Vm sine of omega t for the microphone signal all the time because it may not even be a sinusoid. So we will just call this Vin, the input signal. This is a signal. It's an input signal. It's a voltage. And it's coming from something. It could be a microphone. It could be a digital camera. It could be anything else, right? And we would like to amplify that. Okay. All right. Now what we noticed was that when we apply the signal here, and the signal is small, the collector current is equal to the original current in the absence of a signal plus Gm of the device times this voltage that we have added on top of the bias, provided that this is a small voltage. So Gm times Vin. What I just showed you a moment ago had Gm Vm sine of omega t, because Vm sine of omega t was the voltage of the microphone, which we now, for simplicity, call Vin. All right. So this is what we have. We have a bias voltage for the base emitter, and in response, we have a bias current in the collector. On top of that, we have a signal voltage, Vin, and in response to that, we have a signal current, GmVin. These two are added together here. These two are added together here. So in a sense, we're doing superposition. Remember how superposition works in circuits, right? We have one stimulus, one input, we get another one output. We have another stimulus, we have another output. If we add these two stimuli, we also add the outputs corresponding to the stimuli. So we can say that these are two different stimuli. A constant value is some sort of signal value. And then in response to these, we also have a constant value and some signal value. So maybe what I can do is I can consider this whole circuit with all the stuff in it as two different circuits. So we will say that this is equivalent to two circuits. One that looks like this. It has only bias values in it, V0 and VCE, and a current which is equal to IC0. That's it. A circuit with no signal, just biases. And then another circuit, in a sense we are adding these two circuits, although this is sort of a funny addition. You cannot really add two circuits, but you know what I mean. So here's one response that comes from DC, and then we have another response where we have a microphone. I will call that V in. So this is like the microphone, if you like to think of it that way. And then in response to this, we also have a current, which we called GM V in. So if that causes too much confusion, let me just draw the microphone again so that we have the same thing. So here's a microphone, and here's V in. All right, so I won't bother with this part for now. Don't worry about it. I'll come back to that in a moment. So don't think about this part for now. Okay, so what this says is we can consider these as two circuits with different stimuli and different responses, such that if we add the stimuli, the inputs, when we add the responses, we get what we had in the original circuit. So this has, the circuit on the left has only a bias voltage for the base emitter junction and only a collector, a DC current for the collector. The circuit on the right has a signal voltage between the base and emitter, and then it has a signal current. So in a sense, it's superposition, right? I have this scenario, I have this scenario, I add the stimuli, I have to add the responses. So I add the stimuli, I have to add the responses. Okay, what happens to this guy here? Well, again, when I went from here to here, I'm only drawing the signals. I'm not drawing the DC values. So we'll just do that for now. Okay, I know it's a little confusing. Don't worry, we'll come back to that later. Okay, so if I am given this circuit and I'm asked to calculate IC0 if I know V0, I know how to do that. I use the large signal model. I have an exponential here, calculate, and so forth. So for the large signal model, we draw that here. And this is IS x of VBE over VT, and so forth, right? So we have a V0 voltage here, we have this voltage here, and so on. We can do the calculations as we have seen in the past. And that will give us IC0. So we can find IC0. So for bias calculations, I used the large signal model. Why? Well, because this base emitter voltage is not small by any means, right? This base emitter voltage is 750, 800 millivolts, so that's not much less than VT. So I have to use the large signal model, even though this is not really a signal, it's just a DC value. Okay, how about this one? What do I do here? So here's the input signal, plus minus V in. Again, think of the microphone as just a voltage source, the voltage source whose value is changing with time according to the signal from the microphone. So how do I model this guy here? Well, it is drawing a certain current. And in fact, the current it's drawing is equal to some number times this voltage. What do we call that? We have something that draws a current, and that current is proportional to some voltage. We call that a voltage-dependent current source. So we draw a voltage-dependent current source here, and we call that GM-Vin, and Vin happens to be this voltage here. So we call that Vin here. Right? So all I did is try to replace this transistor with something that should make sense if we think about it carefully. So I'm trying to model the transistor by this dashed box. Okay, so lots of surprises here. Number one, we do not have an exponential dependence. It's Gm times Vin, Gm times this voltage, not exponential of Vin over Vt, etc., right? Why? Well, this is because we decided to decompose this into two. One is a constant value, which has a exponential dependence on V0, and another, which is a linear term, because it's linearly proportional to Vin. And that is what we get here. This is just a current that is linearly proportional to a voltage. A current source whose value is a constant like K times Vin. So that's what we see here, which is very interesting and yet strange. Now, another way of remembering that this is a linear term is if we go back to what I just showed you here. Now remember we said we approximate this little piece here by straight line. So if this is a straight line, then the dependence of this current change upon this voltage change is linear. So that's why we have Gm times the input voltage, right? So in other words, what I'm doing here is this calculation corresponds to finding the relation between this voltage and this current. And then this calculation corresponds to finding the relationship between this voltage fluctuation and this current fluctuation. So these are superimposed on each other. We are using superposition because the system is linear. The system is linear only in that I have a constant current, and on top of that I add a small perturbation. Okay, or I have a constant voltage for the base emitter voltage, and on top of that I add a small perturbation. So we have this linear approximation here. Okay, so what we are thinking is, if we call this the large signal model of the transistor, then we should call this the small signal model of the transistor, because it's valid only if the change in the current is small. Remember, that's how we managed to separate this into one constant term and one linear term. So we'll call this the small signal model of the transistor. Okay, the second surprise here is that the base is open circuit. That's a little strange because we know that the base does draw a current. It's a small current, but it does draw a current. We said that the base current is equal to the collector current divided by beta. So what happened? How come this is open? Well, maybe it's not correct. So let's go back to fundamentals. What we do remember is that the base current is equal to the collector current divided by beta. Now, if the collector current is equal to IC0, a bias value, plus a signal value, then the base current should have something similar in it. So then it would be equal to the bias value divided by beta plus the signal value divided by beta. All right. The bias value should be taken care of in the corresponding model, the small signal, the large signal model. And that's fine because I have a diode here. This diode does draw a current, and by proper choice of IS of this diode, I guarantee that this current is this current divided by beta. No problem there. But how about here? Well, here we need a current of this much. So this terminal has to have a current that flows, and its amount is this value. So what do I add between this point and this point so that it draws this much current? So we're looking for some sort of device, hopefully a two-terminal device. Right? I'm looking for a two-terminal device to connect between these 2 points such that when this voltage is V in, the current flowing through this, the base current flowing through this, is GMV in over beta. So here's the problem by itself. Okay, so don't worry about the transistor for now. This is what we have. Some sort of device, we don't know what it is. And we measure the voltage across it, it's V in. V in from here to here. We measure the current through it, the base current that's necessary. It comes out to be this. So the current is GM V in over beta. So what kind of device is this? Well, what's interesting is that the current is linearly proportional to the voltage. That would be a linear resistor. So maybe this is just a resistor. So then maybe this is what we need. We have a resistor here. The resistor, we have to connect the resistor between these two. And how much is the value of the resistor? Well, that's V, that's I. We divide V by I to get the current, the resistance, right? So you can see that if you divide V in by GMV in over beta, V ins cross out, and we end up with beta over GM. So the resistance value is beta over GM. Okay, so let's carry everything we have learned here to the other side of the board. So we write this as more complete small signal model. And this is what we observe. We have a resistance of value beta over GM, a voltage dependent current source GM V in, and V in is this voltage, and that the current is coming from here. This is the collector terminal, this is the emitter terminal, and this is the base terminal. All right, so this agrees with what we have found so far. We have the voltage difference between base and emitter equal to V in. This is the small fluctuation coming from the microphone. And in response to that, we have some current fluctuation, which is modeled by GM times V in. And that's this one. We need some base current. The base current has to be provided, drawn by something like a resistor. So we have the resistor, and we found the value of the resistor that satisfies that. All right, so in general, we will slightly change this to write it in the form that is common in our language. So here's the more general model that we draw. We have a resistor between base and emitter. See, this is just one line. It's all connected together. It's a short circuit, right? So base is here, emitter is here, and collector is here. Okay. Now I don't want to write beta over GM every time, so I will give this resistor a name. And that name is R sub pi. Because it comes from something called the pi model, etc. We don't worry about it here. And then I don't want to call this V in, this one, because V in could be something else. V in could be some input voltage somewhere else. So we want to give it a specific name that is always representative of the base emitter voltage. the base emitter voltage fluctuation. So we call that V sub pi. And it's positive here, is here, and it's negative is here. So then, if this voltage is called V pi, this current has to be Gm times V pi. So this is the model that we use for a bipolar transistor. At least for now. It's not complete, but it's pretty good. So when you see a circuit and has some bipolar transistors in it, and you would like to see how these devices respond to small signals that are coming through them and going through them, then you can construct this in your mind and see what happens. All right? Okay, so in summary, if we are given a circuit that has some bias components and then some signal components, we study this circuit in two phases. One phase, we consider only the constant voltages that are applied to the device and see how much current flows through each terminal of the device when we have these voltages around it. For that, we use the large signal model because this voltage is not small compared to VT. This current is the current we're trying to find, so we have to use the actual model. Now, if after we find these quantities, we now go over and try to, in the second phase, calculate the response of the circuit to small signals that are coming in, and these signals are above and superimposed on the DC voltages that we had before. So we had a voltage here, superimposed on that we have a signal. And this tells us the response to the signals. At the end, what we have is really the sum of the two. We have some bias value flowing through the collector, and then we have some signal, which is the result of the input signal. So for finding the response to the signal, if the signal is small, we use the small signal model. Okay, so let's see now what we should do. Okay, let's just look at an example. Find the small signal model of a linear resistor. So very simple. I give you a resistor and I ask you to find the small signal model. You say, okay, well, I know that the resistor satisfies Ohm's law. So if I take a resistor and I give it a certain voltage, Vx, and I measure the current that flows, I know that the relationship between these two is a straight line. So we have a straight line here with a slope of 1 over R1. I apply voltage, measure the current, that's the graph of it. So now if this voltage changes by small amount, so let's say the voltage is already 1 volt, and now it changes by a few millivolts. What happens? Well, if I change the color of my pen, so let's say we are sitting at a voltage of 1 volt, and now we begin to change. Then we are confined to this area, and we have some change in the current. What do I know about the change in the current versus the change in the voltage? Well, this is a straight line, so it doesn't matter how large this change is. Whether it's a very large fluctuation or very small fluctuation, the relationship between this change and this change is always the slope of this line, and the slope of this line is constant. So regardless of what's going on, we can always say Ix is equal to Vx over R1, Or if you are interested in changes, we can say delta Ix is always equal to 1 over R1 times delta Vx. So in contrast to a bipolar transistor, a resistor, a linear resistor, has the same model for large signals and small signals. It doesn't make any difference. For a bipolar transistor, we had to come up with a small signal model because we had an exponential relationship. So we said that we have this type of behavior, and what we see is that the slope is not the same everywhere. So for a small fluctuation here, we get a fluctuation in the current, but the relation between this fluctuation and that fluctuation depends on where we are. And when we make an approximation, this approximation gives us some GM here. This approximation gives us a different GM here. Okay. All right. So if I give you a transistor and you bias it and you find the bias values, do you know how to construct the small signal model? Yes. We know that GM is equal to IC over VT. IC is the bias current, so maybe it's called IC0. So that's GM. For example, if the bias current is 1 milliamp, GM would be 1 milliamp over 26 millivolts, approximately 1 over 26 ohms, they're approximately 40 millisiemens. All right, how about R pi? We also know that because that's just beta over GM. So if we calculate GM to be 1 over 26 ohms, and R pi and beta is 100, then R pi will be 2,600 ohms. So the key idea here is that to find the small signal model, we first need to calculate the bias conditions. If it's the bias conditions that will give us how much bias current we have, from the bias current in the collector, we can find the GM, and from the GM, we can find the R pi. So for any small signal analysis, we also need to know the bias calculation, to perform the bias calculations first. All right, so let me make a note of that here. So to find the small signal parameters, we must first calculate the bias conditions. Bias conditions means the base emitter voltage and the collector current. The collector current is really the most important value that appears in all of these equations. All right, now let's go ahead and answer one more question, which is quite important in our calculations. So the question is the following. What happens to batteries in small signal operation or analysis? By batteries, I mean constant voltage sources. Okay, well, we just go back to what we had here, and that will tell us what happens. In fact, we already made an assumption about that and moved on, but we never explicitly talked about it. When we started out, we had a battery and a microphone. a signal source and a constant voltage. And we said, well, we are separating the operation into two. One is just a bias calculation, and one is signal calculation. So for bias calculation, we kept all of the constant sources. And when we went to signal calculation, we said, well, we already took care of the bias calculations. We are only interested in the perturbations, in the signal changes. So we took these out. And when we took those out, we ended up with just a microphone. So when we draw the small signal model of a transistor and eventually of a complete circuit, we set all of the constant voltage sources to 0. You see that this disappeared here. In fact, when we went from here to here, we set this to 0 because we said the small signal model represents only perturbations, only changes in the base emitter voltage and the collector current. A battery doesn't have perturbations. A battery has a constant voltage, so it does not play a role here. A battery does not carry a signal, right? It's always constant. Similarly, for this voltage. So this voltage eventually became a short here, because when we set a voltage source to 0, by definition, we must replace it by a short circuit. So the answer to the question is, replace them with a short circuit, because a 0 voltage source is equivalent to a short circuit. This is important to remember. All right. So, for example, if we have some sort of circuit that has a power supply, the power supply is a constant voltage. So that constant voltage is always set to 0. Now, sometime later, we might see current sources as well in our circuits that are constant. If a current source is constant, again, for small signal operation and analysis, its value should be set to 0 because it doesn't have any perturbation, it doesn't change with time. And we know that a 0 current source is equivalent to an open circuit. So from basic circuits, you remember, a 0 voltage source is equivalent to a short circuit, a 0 current source is equivalent to an open circuit. We'll get there, and we'll talk about that at some point. All right, so now that we understand this procedure, we can go ahead and, as an example, try to construct the small signal model for some particular circuit. So let's go ahead and add a page here. And we also change the color of our pen. Okay, so let's look at an example. The example that I have here is this. This is a circuit that we briefly looked at before, and we saw that the calculation of the current was a little difficult because we had to iterate. So we have a bias for the base emitter equal to V0, or a bias for this overall potential. Then we have a signal from the microphone. We call it Vin again. And we have a battery here, VCE. And then we would like to construct the small signal model of the entire circuit. So we replace the transistor itself with this small signal model. And then we also replace the constant voltages by short circuits, by 0 voltage sources. So this is what it looks like. We have, for the microphone, we'll model the microphone by a voltage source. So the microphone remains because that's the signal. That's the perturbation. This battery goes away. It becomes a short circuit. For the bipolar transistor, what do we have? Between base and emitter, we have R pi. So here's R pi. The voltage across R pi is called V pi. So V pi. Between emitter and collector, we have a current source, Gm times V pi. And in this case, we happen to have a resistor from emitter to this point. So we have to draw that resistor in here, R1. And then we said that any constant source is set to 0 in small signal analysis. So that is set to 0. It becomes a short circuit. This is the small signal equivalent circuit or small signal model of the original circuit. Okay, so it's important to remember a few things. It's important to remember that, let me change the color of my pen, that this V pi represents the signal quality or signal quantity or the component that appears between the base and emitter. In other words, is the change in the base emitter voltage. The base emitter voltage already has a bias value, some bias value here, right? But now on top of that, we bring a signal. So this V pi represents the change in VBE. So this is change in VBE. Or sometimes we call it perturbation in VBE. Similarly, this current source, which is represents the collector current, is this guy here, represents the change in IC, the collector current. So IC, without a signal, is equal to some amount, which we call IC0. Now, when the signal comes in, that current begins to change, and that change is what we call GMV pi. It's always good to remember that we have two different models. One model for bias calculations, one model for signal calculations, so to speak, meaning the response to small perturbations. All right, this is a little example. The next example is our quiz. So here's a quiz. We would like to draw the small signal equivalent circuit of what I will show you. So here's what we have. So again, we have a microphone, we have a battery here, and then we have a resistor up here, and then we have another battery here. So this is the microphone, we call it V in. This is the battery, we call it V0. And we would like to construct the equivalent circuit of this. I'll call this V1. So I'll give you 90 seconds to calculate this. Okay, so what did you find for the small signal model? Well, we start from right here and we say this is a signal voltage source, so we have to keep it. It changes with time. So here's our signal source. We model it by Vin. This voltage source does not change with time, it's constant, so we set it to 0. That's gone. We have a bipolar transistor, so a small signal model is known. We have R pi between base and emitter. Then we have a current source, so R pi here. The voltage across R pi is called V pi. The current source is a dependent current source, GMV pi. The emitter connects to this point directly. We don't have any resistors in this example. And then the voltage source connected from up here to here is set to 0. We have a resistor that goes from okay, that's a bad drawing. Let's clean that up. So we have a resistor that goes from the collector up here. We call that R1. Remember that the small signal model of a resistor is the same as the large signal, so we always just draw a resistor. And then this voltage source is a short circuit, so we have this. And if you don't like this extra wire here, we can erase it to make it clearer. Okay, so that is the small signal model of the transistor and the rest of the circuit. Later on we will see that using these types of models we can analyze circuits much more easily than having lots of exponentials and things lying around. Okay, let's see. Now, if in a given circuit we have some bias quantities and then some signal quantities, how do we distinguish between these two in our notation to avoid confusion? For example, I may have a base emitter voltage, which is the bias value, or I may have a base emitter voltage, which is the signal quantity. So the convention that generally is accepted in our electronics is as follows. So we say large, let's go back here. We say, so this is the notation that we use. So large signal quantities including bias quantities are represented by uppercase letters. Uppercase. So examples would be Vn, IC, VBE, VCE, etc. So this Vn, if it's written like this, means that it's large signal. It can be anything. It's not a little tiny signal from the microphone. It can be 200 millivolts, 300 millivolts, or something, right? So that's the notation. For small signal quantities, if we know that they are small signal, so small signal quantities, as you might expect, we use lowercase letters. So lowercase. So that would be, for example, Vn, IC, VBE, VCE, and so on. So that's just a quick notation that is good to remember. Now, what really happens is that we try to be careful, especially in a course at this level, to distinguish between these two notations. But the reality of the matter is that when you go into the field of electronics and you become a professional in that field, eventually you don't really make that distinction. Okay? But for now, we will be careful with that. All right. So that's our notation. And now we are ready to talk about early effect. Okay, so let's remember what the characteristic of the bipolar transistor looks like when we consider IC as a function of VCE. So what we remember is the following. If I take a bipolar transistor and connect a constant base emitter voltage to it, but use a variable voltage, sometimes we draw the variable voltage by a circle. That's the official notation. Sometimes we can draw a battery and put an arrow into it, across it, to show variability. But anyway, so VCE. We said that if this voltage is variable, then the current doesn't vary. That's what we said, right? And that's why we decided that this entire circuit can be considered a current source. Now in reality, if we go to the lab and build the circuit and perform this measurement, that's not what we see. In reality, what we will see is the following. So let's change the color of our pen. We see that this actually goes like this. It has some variation. So that's interesting. Why does this happen? Now, we are curious to see why it happens, but more importantly, we are curious to see how this affects our circuit analysis and design later. And that's why we need to have some understanding of the inner workings of the transistor, the internal operation of the transistor. So let's go ahead, let's go inside the transistor and examine exactly what happens as the collector emitter voltage increases. Maybe we can figure out why this current goes up. All right, so here's the bipolar transistor. As usual, we have an N piece here, a P piece here, and an N plus piece here for the emitter. And we forward bias the base emitter junction. We connect another voltage source between collector and emitter, and we make that positive enough to VCE. And we have a certain base emitter voltage, VBE. So what we said was lots of electrons take off from the emitter, cross the depletion region to the base area, the base region. Then they go and get close to the depletion region around collector emitter, and they are quickly absorbed and accelerated, and they go through to the collector. They are collected by the collector. So we said that there's a depletion region here, and the density of electrons is very high at this point because they have just entered from the emitter into the base, and that density goes down to close to zero by the time we get to the edge of the depletion region from the base to the collector. So this is the concentration of electrons as a function of distance. Okay? All right. Now let's go ahead and increase the collector emitter voltage. So we are, let's say, over here. Now we go over here. And remember that this is a reverse biased junction. What happens if we take a reverse biased PN junction and make it more reverse biased? As this voltage goes up, we have more reverse bias because this is more positive than this. Well, we said that the depletion region around the junction becomes wider. So as VCE goes up, this dashed line, which represents the edge of the depletion region, goes away from the junction, meaning that the depletion region becomes wider. So let's change the color to maybe this and draw that again. So we have a situation like this as the collector emitter voltage increases. On the other side as well, but we're not interested in that side. So as VCE increases, the depletion region becomes wider. So now, if the depletion region starts from here rather than here, what happens to the density of electrons as a function of distance? We still have a high density over here, but the density of electrons should drop to close to 0 over here, not over here. Right? So what we see is that the density of electrons drops to 0 over here. Now, which one of these density plots has a sharper slope? We see that the second one has a sharper slope because this point hasn't changed, but this point has come to the, towards the emitter. That means that the diffusion current of electrons flowing this way through the base increases because the slope increases. Right? The concentration gradient has increased, so the diffusion current has to increase. And that's why the current increases. So as the collector voltage goes up, this depletion region creeps this way. The actual base width, the effective base width decreases, and as that decreases, the current increases. And in fact, if we write the equation for the collector current, we also see that. Remember that we have IC is equal to IS exp of VBE over VT. And we said that this IS is given by the area times Q, charge of the electron, Ni squared, times dN, diffusivity of electrons. And then we had the doping in the base, and then we had WB. If you remember, WB was the base width, meaning from here to here. So what we see is that as the collector voltage increases, the base width decreases. So this decreases, IS increases, IC increases. So interestingly, IS itself is not constant. It's actually a function of the collector voltage. All right, so then how do we modify our equations to reflect this behavior? If you really want to reflect that behavior here, this would be complicated because WB now becomes a voltage-dependent parameter. So we really don't want to deal with that. Instead, we will make an approximation. Our approximation will be the following. So let me change the color of my pen again, and I will show you what we do. So we say, well, this current is increasing even though our prediction was it shouldn't. So maybe I should play with this equation somehow to create some dependence upon VCE. And the simplest dependence we can have is a linear dependence. So maybe what I'm thinking is, let's take this and multiply it by some linear function of VCE. So that as VCE increases, this whole thing increases. All right, so maybe this is what I will do. I will write 1 plus VCE. Now that's not going to work because this is a voltage quantity, this doesn't have a unit. So I have to put a coefficient here, and that coefficient will be of this form. VA, V sub A. Now you can see that as VC increases, IC increases. And the increase is linear, so it goes up linearly. All right, what is VA? Well, VA is a property of the device itself. When we buy the transistor, it has a certain VA. VA is called the early voltage after early. So this is called the early voltage. And its typical value is a few volts to a few tens of volts depending on what type of transistor we buy. So now we have a better approximation of what the transistor actually does if its collector-emitter voltage changes. All right, so we don't have that exponential anymore. All right, now if we have an equation like this for the collector current, what happens to our small signal model? We have to go back and revisit that. In our small signal model, we said GM is equal to IC over VT. Is it still true? We said R pi is equal to beta over GM. Is it still true? And then we said we have a current source that is voltage dependent, GM times V pi, and nothing else between collector and emitter. Is that true? So all of those have to be re-examined in light of what we have discovered in terms of the early effect. So we'll get there and we'll do that. But this is what we have in terms of the large signal model of the device. This is called large signal because VCE can vary a lot, VBE can vary a lot, and this is still valid. Of course, as long as we are in forward active region. Okay. All right, so our time is up. Next time we will go back to the small signal model and see how early effect should be considered and included in the small signal model. And from then we will have a model that we can work with, and then we will look at some other types of bipolar transistors. I will see you next time.